Welcome to the last segment in the lecture on bioremediation and bioaugmentation. We've gone through the biodegradation potential of chemicals, some of the redox issues in application of in situ bioremediation, talked a little bit about the microbiology and biochemistry, and we identified that bringing the contaminants together with the additions and the bacteria was the real issue that contaminant hydrogeologists had to solve. And we showed a number of ways that you could approach this problem. Now we want to talk a little bit about chlorinated solvent bioremediation, and that'll get us into bioaugmentation. So remediating chlorinated solvents in situ can be done by a number of techniques. Some control technologies, reactive barriers, in situ chemical oxidation, and biological degradation. The in situ bioprocesses are different than the ones we've seen for petroleum hydrocarbons in that our job is to add electron donor to drive the system anaerobic, and in those conditions chlorinated solvents like TCE are more likely to biodegrade. We can actually do this in source zones where there's residual NAPL, and we can enhance the effective rate of degradation of those source zones. And some evidence suggests we might get a 2-fold to an 8-fold increase in the rate of degradation by developing an active biodegradation population in the source zone itself. Consider our job is to increase the flux from the NAPL across the stagnant film into the flowing groundwater. We want to remove the residual as quickly as possible. So here's a cartoon that shows us what it might look like. Here's the residual. There's a sort of a stagnant layer and a flowing groundwater layer. We normally assume that the water is saturated with respect to the NAPL at that interface. At some interface, at some distance away, the concentration is now the concentration in the flowing groundwater. So you can see if we can increase that gradient, we can increase the N, and so that's what we're trying to do. Can't increase the gradient beyond the saturation value unless we add surfactants and things like that. That's not shown to be too effective. Let's see if we can affect CW, the concentration in the water phase. Let's lower that and get a higher gradient and therefore a faster rate of mass transfer. How do we do it? Well, we stick a bacteria right at that interface. Perfect spot for a bacteria. Gets contaminant diffusing out of the stagnant film, and it has remedial solutions coming in. So as long as we can keep the remedial solution and we have bacteria that are active, the concentration at that interface is now lowered. Lower concentration, higher flux. So not only do we get the NAPL dissolving more quickly, we also get to degrade it before it gets into the plume. Well, what approaches could we use for chlorinated solvents specifically? If we have aerobic conditions or wish to stimulate aerobic conditions, we could expect that the highly chlorinated compounds, PCE and TCE, won't degrade. There's some potential, so we could add things like methane and toluene. Well, if we have aerobic conditions and we're adding oxygen and methane might be an explosive mixture above the ground. Toluene's a contaminant, so co-metabolic systems aren't really favored. Turns out that the less chlorinated, less oxidized chlorinated hydrocarbons are more degradable aerobically. So under aerobic conditions, we might get some TCE and vinyl chloride degradation. What about anaerobic conditions? Here we can get quite rapid PCE and TCE degradation. The common experience is that the products of that degradation, the dechlorination products, DCE and vinyl chloride, accumulate. That suggests to people doing reactive barrier treatment, for example, where they have a sequential barrier, where they can do one treatment then the other, that it's probably best to do an anaerobic treatment first to dechlorinate PCE and TCE, and then if you have to, switch to an aerobic treatment, down gradient perhaps, to get rid of the accumulating DCE and vinyl chloride. But under anaerobic conditions, if a certain group of bacteria, Dihelicocoides, is present, they can also degrade DCE and vinyl chloride. And people have developed a number of cultures from natural systems in which this group of bacteria are active and can do all of the dechlorination anaerobically. So what approaches could we do? Well, there's really two approaches. First is to add electron donors to drive the system anaerobic, create methanogenic conditions, and those will promote dechlorination reactions. So we suggested PCE and TCE may stop at DCE and vinyl chloride. What do we do when the system's stuck? There are two possibilities. One is to simply keep adding electron donor and hope that the capability develops. That may be an approach where some metabolites and some microbial population assessment would be well worth it. If you thought there were Dihelicocoides bacteria present, then there's a good chance that you could stimulate them, and this approach might be one of them. On the other hand, if there are no Dihelicocoides present, there might be a real advantage to simply add them. So that's the second approach, to bioaugment. There's a very good discussion in the literature a few years ago about these two different approaches. It was a response by Dave Major and his colleagues to a paper by Evan Nair and his colleagues. Nair was proponent of the first technology, simply keep adding electron donor and things will work. And Major was suggesting that bioaugmentation with a culture would be a better approach. So again, we're not really sure which is the best, but it's a very interesting discussion and I certainly recommend it to you. So Nair really said, just keep throwing in electron donors and the ability will develop. Major and his colleagues suggested that where they don't find Dihelicocoides, it's proven to be very beneficial, at least at pilot scale, to add Dihelicocoides. You still have to add electron donor, but the bacteria itself appears to be an important issue as well. Adding bacteria is bioaugmentation. It's the adding of specialized biological cultures to perform a specific remedial task in a given environment. And for us, we're talking generally about in situ groundwater environments. Why? Well, contaminants present, but there doesn't appear to be any bacteria fulfilling the ecological niche of degrading that contaminant. And it also provides more bacteria who can carry out that reaction. That should shorten the time in which it takes for the population to develop that ability. And it should lead to faster degradation with more bacteria able to carry out that reaction. Number of critical issues, and anybody who's doing bioaugmentation should always be asked about these things. Well, how many organisms are they adding? So in petroleum hydrocarbons, at most sites where oxygen's added, the natural bacteria have somewhere between 10 to the 4 and 10 to the 8 active viable organisms operating. So simple oxygen addition gets you 10 to the 4 to the 10 to the 8. Bioaugmentation then has to add a significant number of bacteria. And that 10 to the 4 and 10 to the 8 is bacteria per gram of aquifer material. So to add that much biomass to a sizable contaminated site, perhaps 10, more likely 100 cubic meters, would require a huge addition of biomass. Most bioaugmentation are adding a few bacteria per gram. So unlikely to make a big difference when the natural biological system has that capability already. Do the organisms survive? If you've cultured the organism from a wastewater treatment plant at 40 degrees C and you're subjecting them to a 10 degrees C aquifer, will they survive? Will they survive the normal predation that occurs in the subsurface? It's a tough environment out there. When you add the bacteria, typically through injection of water in a well, do they move anywhere? Are they filtered or highly retarded by the sediment? Are you adding nutrients? Are there enough nutrients? You've added a lot of bacteria, we hope. Do you have to add nutrients as well? Are the contaminant concentrations too high? Are they too low? Are we sure that we've got everything well balanced? So, good questions to ask people that are adding organisms to the subsurface. At least in Canada, there's a concern about potential pathogenic properties of the organisms you're adding. And you have to go through very large hoops to get licensed to deliver microorganisms to the subsurface. So I'm not an expert in bioaugmentation. I've never been involved in it personally. So a number of good reviews. Again, the Clue Insight of the US EPA is a good one. And some specific references. Just mentioned 2 papers that provided some interesting results. Here's a paper looking at MTBE. An interesting pilot scale field study was conducted looking at MTBE bioaugmentation. This occurred at the Port Hueneme site. 2 test plots were developed, down gradient of an MTBE source, and they were both sparged with oxygen, so both had oxygen addition. Plot B was also inoculated with this PM1 strain of MTBE degraders. Although concentrations were quite variable, there was evidence that MTBE was degrading in both systems down gradient of the injection zone. So whether or not they added the PM1 strain, they got degradation. They measured survival and movement of the strain in groundwater samples down gradient, which is good. The PM1 seemed to move quite quickly. Unfortunately, it was also detected outside of the zone where it was added. So somehow it had naturally developed. The natural ability to degrade MTBE was already present. So while they did demonstrate that the strain had an ability to survive and migrate and conduct MTBE degradation, they also demonstrated that when that capability is there, simply adding the electron acceptor was sufficient to get degradation. And they point out quite correctly that if that capability doesn't exist at the site, then a system might be quite advantageous. Another approach was the chlorinated solvent issue. And again, they looked at a comparison of this passive drift approach to active recirculation approach. And after preconditioning, they bioaugmented with the dihelicocoides containing culture. And they did see vinyl chloride then start to dechlorinate. They did get a distribution of DCE in both systems. Their bacteria were shown to move almost as fast as the conservative tracer, so they did actually move without much retardation. And both approaches seem to conduct the degradation with some success. So there's an example, at least at a pilot scale, of dihelicocoides assisting in the in situ biodegradation of chlorinated solvents. So to summarize all of our in situ bioremediation and bioaugmentation, I still think the critical issue is how to bring the additions, whether they be nutrients or bacteria, electron acceptors, electron donors, together with contaminants and bacteria in our in situ efforts. If we can't do all of that, if we can't bring them together, then we probably need to move ex situ or look at a different technology. We're really depending on dispersion in the flowing groundwater system to do most of this mixing. And unfortunately, dispersion in the subsurface is quite weak. So this is really still the critical issue, the critical aspect that hydrogeologists play a key role in. So that's my perspective on in situ bioremediation and bioaugmentation. Thank you very much.